All right, welcome to Module 5, Part 2. We're going to talk about natural building structures. We're going to avoid a conventional building structure, which is your standard wood framing, exterior material. You have your interior materials, which could be sheetrock or plasterboard, and then some type of insulation in the center. And so that's your standard. Now we're going to talk about these natural building materials and some of the older forms of building materials, and then what the future is looking like. And the nice thing is we are getting a little bit more experimental. No, I'm not going to go into any of the funky stuff that's built with a tire or plastic bottles or any of that. Those are novelty. I'm talking about things that have been built, work, stand up to various climate conditions, and probably will continue to stand up to climate conditions as we utilize them in the future. And so one of the first and oldest methods of building is adobe cob. Adobe cob was originally done with things like dirt and straw, and you would mix it into this clay mixture that we can then harden into bricks that could be cut and stacked, or we would create troughing and actually place it in the troughing and ram it down, and that's rammed earth. Now, rammed earth is the next slide, but it's following the same concept of adobe cob. So adobe cob is more like cut structure that's then stacked. And when you think of the Great Pyramids, the exterior of the pyramid is marble, but the interior and what they stacked the marble on top of was an adobe cob structure that they would cut the bricks and then stack up the pyramid and then place the marble on the exterior. And then this is a Mesa Verde building, obviously adobe cob, that you can find out in the Mojave Desert right here in the United States. And these are 300-400 years old, and they're still standing today. And adobe cob do fabulous and incredibly dry weathers because as they continue to heat, they just continue to dry out. And so they work really, really well. With that said, it's not uncommon to see adobe cob in other forms in wetter climates. And I'll show you some of those as we continue on. So that brings me to the concept of rammed earth. Now, rammed earth you could do in multiple ways, but one of the easiest techniques would be to build two troughs on either side and place in your clay structure with straw sometimes within it. Sometimes you don't use straw so that the material doesn't fatigue, and that's if it is truly clay and it's not kind of silt particles, larger soil particles, and then you ram them down, squeezing out any moisture and any airspace, creating what's called a pavementing. You are creating a true pavement, or when you think of that nice little cow patty that goes across the quad, that area where everybody has walked so many times that it's just so hard and dry that it's impermeable at this point. One of the most famous structures that is mostly rammed earth is the Great Wall of China. There are exterior parts of the Great Wall of China that are lined with stone, and those are the ones that we see in images that have that very picturesque concept. But most of the Great Wall of China and the interior parts of the Great Wall of China is a true rammed earth. And here's a modern day rammed earth building. Here they built the troughing, and they actually put in their clay lining in various colors to kind of create that desert canyon wall effect along it. And they even inserted in these lovely granite slabs to create areas for windowing in the structure. And it's just a beautiful building structure that they have in this concept. And here is another building, and this one they obviously lined with the clay. So they dyed out the clay as they put it in and created their rammed earth. And it's just absolutely gorgeous. But it's one continuous line, if you notice that. So they built like a little trough line and boarded it and then did the rammed earth within. And these both are modern day structures. So these were done with hydraulics in modern day. And just gorgeous building technique and fabulous for dry weather. One of the most famous and wonderful forms of technique building is timber framing, and true old timber framing, where I take wet wood, so wood that has not been cured and dried, and I cut in my framing for my archetype, and then I set my frames in and I let the wet wood dry. And when it dries, wood expands as it loses moisture. And so when it expands out from losing its moisture, it will then wedge itself together, creating things that do not need pinholes or other structures. And here's a beautiful modern day timber frame. And this one's going to actually be a standard kind of barn that was built. This is called the Harmony House. This is out in Slippery Rock, Pennsylvania. And this was the structure for the Harmony House. And once again, you can see there's no metal framing, no pinning in there, nothing like that. All of it's wet wood framing, just gorgeous in there, just set right in. Here's some more timber framing. And these two right here are timber framing that also have straw bale in between. So this is the timber frame with the straw bale construction with exterior claying to put into place, right? This is our standard building structure in 1500s, 1400s. And then modern day, absolutely beautiful. And it's making a comeback. And the beautiful thing about the art of timber framing is that while it's making a comeback and it's gaining all of this information, we have all this old information that we can use as technology to build off of. And there's money in it. It's something that is appreciated and artisaned, and people will spend the money and the time to do properly. So that brings us into a little bit of home energy conversion and heat transfer controls. When we look at things like housing, we look at the insulation with it, we can then calculate out heat within the building. And all building materials can be evaluated as an exchange of heat based on their R value. And the way that I will look at a building material is I will look at its QC, which is thermal. C is specific heat, so it's thermal specific heat divided by the time that's spent. This is equal to 1 divided by the R values, and that would be the sum of all R values, times the area times the change in temperature. So the temperature versus the temperature outside, so inside versus outside. Looking at those R values, every item has a set R value. And so here we go. This is my list of the R value. And if I double the thickness, I double my R value number. So if for some reason I have my hardwood and I have 2 inches of hardwood instead, I'm going to add my 0.91 plus 0.91 because I've doubled my R value and I have to travel through all of that material. When we do any equation looking at all of this, I have to look at the R values summed of all the material that I'm going to travel through. So if I'm traveling through the plasterboard, I have to do the plasterboard, then my insulation, then I have to do my soft wood on the exterior, and then whatever my outer siding is on the outside. So I have to add all of those R values together to get a total R value that then would divide into my 1 divided by my sum of all of those R values. So for example, if I'm looking at an equation for this, I can calculate the total heat transfer for 24 hours through a brick garage, 2 inches thick, that measures 15 by 20 with a heating of 55 and an outdoor temperature of 12 degrees Fahrenheit. So I'm going to clean up my equation so that I can put everything in the box. So first I'm going to figure out my area. So I do 15 times 20, I get my 300. And that's feet squared. That's going to go where the A is. I'm going to find my change in temperature. So I'm going to subtract my indoor temperature minus my outdoor temperature, which is a change of 43 degrees Fahrenheit. And I'm going to pop that in right there. I'm going to sum up all of my R values. Now notice it's 2 inches thick on my garage, so it's a brick and it's 2-inch thick brick. So I'm going to take 2 inches and times that by my 0.20 because on my table, the brick is based on 1 inch, right? It's based on 1 inch right here. So I'm going to times it by 2 and use 0.4. This is my units, and then I get my answer of 0.4. And I can plug everything into my equation, and then my final step will be to divide it by 24 hours. So when I times all my numbers up, I end up with 32,250. And then I'm going to divide this all. I'm going to move the times to the other to get an hourly number. And so I'm going to move this over 24, and I'll have to times it. So times that by 24 hours. And my total final thermal number is 700.